Hello, everyone, and welcome to today's live broadcast, Real-World Tips for Managing a Successful Life Science Lab Redesign, presented by Matt Anderson and Brian Garrett. We're excited to bring you this educational web seminar presented by LabRoots and sponsored by Labconco. Serving the scientific community since 1925, Labconco manufactures laboratory equipment, specializing in ventilation products such as chemical fume hoods and biological safety cabinets. Other product lines include glassware washers and freeze dryers. Labconco has ISO 9001 certification, one measure of the company's commitment to quality and consistency in design and manufacturing. Labconco equipment is manufactured in Kansas City, Missouri and Fort Scott, Kansas, and marketed worldwide to academic, industrial, life science, pharmaceutical, environmental, forensic, and clinical laboratories. To learn more about Labconco, please visit www.labconco.com. I am Judy O'Rourke of LabRoots, and I'll be your moderator for today's event. This webinar has been approved for continuing educational credits. Please click on the CE button at the bottom left corner and follow the process to receive your credits. Before we begin, I want to let everyone know that this event is interactive. We encourage you to participate by submitting as many questions as you want at any time you want during the presentation. Just click on the green Q&A button located in the lower left of the presentation window and type your question into the box that appears on the screen. We'll answer as many questions as we have time for at the end of the presentation. Also, please notice you'll be viewing the presentation in the slide window. To enlarge the window, just click on the screen icon located on the lower right. And finally, if you have trouble seeing or hearing the presentation, please click on the support button at the top right of the presentation window, or you can use the Q&A button to let us know that you're having a problem. Thank you. Now I'd like to introduce today's speakers. Matt Anderson is the Biosafety Officer at University of Nebraska-Lincoln in the Department of Environmental Health and Safety. He has a doctorate in chemical biology from Washington University in St. Louis and completed a one-year postdoctoral fellowship in biosafety at Washington University in St. Louis. Matt is a registered biosafety professional through ABSA, and he is active in ABSA International and Mabion, the Midwest Area Biosafety Network. Matt serves as co-chair of the ABSA International E-Communications Committee and as president of Mabion. He has participated in numerous lab design projects while at the university, ranging from new chemistry teaching labs to biological research labs to a high-containment animal biosafety level 3 lab. Brian Garrett is the product manager for Biosafety Cabinets and Ductless fume hoods at Labconco Corporation. In 2010, he was accredited as a lead green associate with the U.S. Green Building Council. Before joining Labconco, he was a laboratory director for the Institute for Environmental Health Laboratories in Omaha, Nebraska, where he focused on planning and management of 2 labs in the beef industry, analyzing food-borne pathogens. He is a member of the Controlled Environment Testing Association and the American Biological Safety Association International and sits on the Joint Committee for NSF ANSI Standard 49. Please join me in welcoming Matt Anderson. I will now turn the presentation over to him.
Thank you for that introduction, Judy. Before I begin, I wanted to state that the opinions and perspectives that I'm going to share are my own and not representative of my employer. But I do want to share my experiences as a safety officer and provide some tips for good lab design that I have gained through my experience. So, what are the components of safe lab design? There are several key factors that all have a role in making a lab safe, and I'll touch on each of these in my part of the presentation today. These include design, engineering controls, procedures, personal protective equipment or PPE, and the people that work in the labs. On this slide you see the hierarchy of controls that are used to eliminate and minimize hazards in the workplace. These are also good things to consider when designing or renovating existing labs. Evaluating if an existing space needs to be maintained or if it can be eliminated. If you are in an older space, don't be content with replicating your existing lab with new materials. Now is a chance to rethink, to improve, and to design for the future. Is there a better way to do things? Is there better equipment out there? Are there better processes? Now is your chance to make a change for the better. I know a lot of scientists like to argue, I've done it this way for years. Why do I need to change? Well, the answer is that times are changing. People want to feel safe in their workplace, and the public is starting to demand safe labs so they feel safe outside the labs and can be assured that nothing is going to get out and harm them. The first question to ask is, can the hazard be eliminated? Do you have to work with that chemical? Do you have to work with that material? If you don't, then eliminate it from your process. The same can be said of the design components. If the piece of the lab is outdated, if you don't need it, then eliminate it. Is there a better solution out there? Substitution is the next step. If there's a less hazardous chemical or a less hazardous material for the material that you're working with and the process you're working with, then you use that instead, so the hazard is reduced. If you can't eliminate or substitute the hazard, do you have appropriate engineering controls in place? Are you working in a fume hood? Is there proper exhaust in the lab? If you have proper engineering controls, but they still haven't eliminated the hazard, the next step is to look at your procedures and administrative controls. Do you restrict access to the lab? Do you require material being handled in a certain way? Do you require extensive training to work with certain materials? Those are examples of procedures and administrative controls. The final consideration after all of those have failed to minimize your risk to an acceptable level is to look at the personal protective equipment being used and institute PPE so that workers can be protected from the hazard. So now that we've talked about the steps to take to eliminate occupational hazards, let's move on to discussing the first factor in making labs safe, which is good lab design. Designing a new lab or renovating an existing one should be viewed as an opportunity to fix the shortcomings of existing or former spaces. Design the space to be adaptable to changes in research over time. Try not to design the space for a specific type of research. Sometimes this can result in expensive renovations in the future if a new occupant is put in place. The infrastructure for the lab should be able to handle future needs. Do you have sufficient engineering controls? Containment equipment. Do you have enough fume hoods? Do you have enough biosafety cabinets? Do you have the exhaust capability to handle those kind of pieces of equipment? Are your exhaust needs appropriate? It's technically an engineering control, but it has to be thought of when you're doing the lab design. It's an important infrastructure piece. Is the lab need to be negative to the hallway? Is there directional airflow need to be in place? Do you have enough airflow through the lab? Are there enough air changes to make sure that noxious odors and things like that are exhausted out of the lab and workers aren't exposed to those things? Is the electrical load sufficient? Do you have enough power outlets? Do you have emergency power? Are those outlets that power critical equipment in good locations? Can you put the equipment you want to put in there in the right places so it makes sense and it's works well? It's also important to hire architects that have lab design experience. There are plenty of architectural firms out there that will bid on your project, but they may not have any experience designing a lab. Make sure you get one that has experience building laboratory spaces. Also make sure that you consult with the lab workers, the managers and directors. When you're looking at your lab design, the frontline workers need to have a voice in the design. They're the ones that are going to be working in the lab every day. They're the ones that are going to have the best perspective on what things can be fixed, what things make them feel safer, and will allow them to work more efficiently. And finally, the managers and supervisors need to be involved in this as well. They need to take ownership of the programming and the design of the space. And they owe that to the design and to the workers. So some of the components of a good lab design that I've seen implemented well and I've also seen overlooked in lab design are shown on this slide. And those include designated areas for specialized research. So if you have microscopy spaces or if you are working with radioactive materials or pathogens, infectious diseases, or other high hazards, it's good to have dedicated spaces to those types of research. It's also good to have common equipment rooms for equipment that's shared. And then when you have freezer farms, if you have ultra-low freezers, those put out a lot of heat. It's necessary to have augmented cooling in those spaces. That's something that's important to consider at the design phase, so you make sure that it gets incorporated. Separate tissue culture and pathogen labs are a good thing to have as well, to make sure that those things you're working with in those spaces are contained and not there isn't a risk of them getting out or people that don't work with those getting exposed to those type of things. Also, just as important is having separate office and eating areas that are outside of the lab spaces. It's very tempting for people to take their work into the lab or to take food into the lab if there are spaces for them to do that in the lab. Having separate lunchrooms and then having policies that lab attire and stuff like that doesn't go into those spaces is important to make sure that everybody is safe in the building. And finally, make sure that your finishes are compatible with the research materials. You want surfaces that are easily cleaned and that are compatible with the various chemicals or other processes you may be working with. So open lab design is a topic I want to touch on and has been very popular in design of laboratories in the last 10 or 15 years. The intent with this is to allow for flexibility and to encourage interdisciplinary and collaborative research. The downfall is that it is very difficult to isolate the various hazards that are present when you work in a lab with an open design. As an example, let's say you have 4 researchers and each of them work with a different thing. One works with radioactive materials, another is a chemist that does a lot of synthesis work. You have a virologist, and you have someone that does animal work. They're all separated in the picture of the labs at the top, and there's consideration of going to an open lab design but still maintaining the proximity of these labs. So the questions that need to be asked are, if you are in an open lab design like this, how do you keep those different hazards separated? Is it possible to do that? And second, how does somebody working in lab A on the bottom know what someone working in lab C is working with? And when you have an open lab design like this, it's very important for people to know what their neighbors are working with. Much more important than it is when you have actual physical walls that separate the spaces. Those hazards are very easily transmitted across through that lab space, and it's important to ask those questions before the design gets finalized in this kind of a concept. So we've talked about lab design. The next step is to make sure you have proper engineering controls in place. So what are engineering controls? Well, OSHA defines them as a physical modification to a process or process equipment or the installation of further equipment with the goal of preventing the release of contaminants into the workplace. So essentially these are going to be physical modifications made to spaces or equipment that help prevent exposures or release of a hazardous substance. So let's talk about some engineering controls. So of the ones that are listed here, you have fume hoods, biosafety cabinets, gas cabinets, glove boxes, sharps and safe sharp devices, machine guarding, eye washes, safety showers. What types of these are you currently using? Are your existing controls aging out? Is there new technology that makes your newer devices better or safer? Some of these things you should consider is, are you not using some of these and you should be? What changes do you need to make to get the best and safest lab you can? Eye washes should be plumbed to the sanitary sewer where allowable. You get more damage from a water spill that spills on the floor than the minute amount of chemical that's diluted and goes down the drain. But you have to make sure you check with local building codes and wastewater rules before implementing that type of policy in design. Are the safety showers accessible? Do they meet the ANSI standard? Make sure you don't let them install drench hoses and call them an eye wash. Those aren't sufficient. and compliant with the ANSI standard about eye washes and safety showers. So now that we've talked about engineering controls, let's move on to procedures. Procedures or administrative controls are put in place when elimination or substitution aren't possible and engineering controls are not sufficient to eliminate the hazard. So evaluating procedures is an important part of designing a new lab or renovating existing spaces. It's been my experience that the procedures are developed based on the existing lab design or engineering controls, and there may be a better or safer way to do the same procedure. Technology evolves quickly, and it's important to not design for the past, but to design for the future. So ask yourself, are your current procedures as safe as they could be? Are there better processes to achieve the same result? And remember, do not replicate existing processes and ways of doing things just because that's how you've always done it. So with procedures considered, we also need to think about any PPE that may be required for those procedures. So you may be thinking, why would I need to think about PPE when I'm designing a new lab? The answer is because sometimes the PPE have special requirements like respirators. Also, PPE currently in use may not be necessary if engineering controls and procedures change. So some good questions to ask when you're considering PPE are shown in this slide. What PPE is needed in the lab? Are there infrastructure needs? An example I show here is that for personal air purifying respirators in a BL3 lab, you may need someplace to plug in the batteries to recharge those battery packs. You also may need showers. So those are pieces that need to be incorporated into that design. Are the engineering controls that can be improved so you don't need as much PPE? And don't keep the status quo just for the sake of convenience or for historical reasons. Redesign and new lab design is a chance to innovate and improve things rather than to just maintain what you have existing. So finally, the people working in labs should be considered and consulted when designing and renovating labs. They know how things work and may have really good suggestions on improving design and to make operations safer and more efficient. Making sure the people are trained appropriately, and make sure if you are a lab worker, ask to be involved in the design. Ask your supervisor, contribute your opinions. You're going to be working in this space every day going forward. It's important that those stakeholders consider your opinions too. So just to review, I want to remind you to don't duplicate your current lab. Now is your opportunity to make it better. Rethink how you do your procedures, involve all your stakeholders, and then innovate, don't duplicate. Thank you for your attention.
Thank you, Matt. I will now turn it over to Brian Garrett.
Thank you, Judy. Thank you, Matt. So what we want to look at, as Matt discussed, were the engineering controls specifically. My experience of being on the manufacturer side is on equipment and engineering controls that are meant to keep people safe. And I'm going to look at it specifically from the point of view of biological safety cabinets. I mean, that's my wheelhouse. That's what I had the most experience in. But there are also many other ways. There are other types of equipment, other processes that can be looked at. And before I even get into biosafety cabinets, I'll throw out a couple of them. Vacuum networks are very important. There are a lot of people in microbiology labs that do aspiration. And if you're looking at it, that aspiration, a lot of people like to hook them up to a network. And the concern is if you don't have the proper filters in place, you can cross-contaminate that vacuum network with multiple people's work. So a lot of times what we see in best practices is each cabinet or each process would have its own aspiration system that is portable, it can be cleaned, it's decontaminatable, and furthermore, it's not a shared network that will mess up an entire floor's worth of work potentially. So there are a lot of other examples of looking at flexibility and improvements in design, but again, I'm going to look at it mostly from the eyes of a biosafety cabinet. So why do we want to design for flexibility? There are a couple of different ways. I'm going to look at this through a couple of case studies. We're really looking to see or see equipment that can help with flexibility to fix or replace what's already happened. So a lot of work's already gone into a design of a building, and maybe in some cases brick and mortar already being laid. We need to, and then they hit a snag. Something happens. We'll go over one of those instances how we can fix that. And then for what's happening today, where buildings are a lot longer lifespan than most of the equipment that goes into them. So as buildings age and technology changes, we want to make sure that that is backwards compatible or that the building is forwards compatible. And then mostly, again, for what will be needed tomorrow, looking at what your building's current role or your lab role is now. Is that always going to be the same in 5 years, 10 years, 15, or even 30 years? So you really want to design, if you can, for the lab of tomorrow. So first we're going to look at using flexibility to course correct. And in this case study, we're looking at, there's a company that deals in genetic markers, and the company's called DNA Genotech. This facility was specifically in Canada, in Ottawa. And they called me completely out of the blue. They'd been working on a new lab, and they had questions pertaining to, because they wanted to put in several Class 2 Type B2 biosafety cabinets. Now, I'm going to get into a lot of specifics here, but those types of cabinets are very, very stringent and strict in their exhaust requirements, and to the point where every cabinet needs its own independent exhaust system. And I know this drawing up here looks like a bunch of spaghetti, but what I was really drawn to and looking at was, you see here in the blue, you see 2 biosafety cabinets. I followed their ductwork around. Okay, everything's fine. They're on independent systems, but those 2 independent systems go into a giant manifold, and that is that's a no-no when it comes to lab design. Those 2 cabinets won't play friendly. They won't run correctly. They might get them to run for maybe 5 to 10 months before they start going into alarm and failure mode. So the work was already being done. The building was already constructed. These cabinets were about ready to go in, and the lab manager called me and said, I found out that, through talking with other people, that I can't do, this design doesn't work for my biological safety cabinets. What can I do? There's a new biosafety cabinet out there called the C1. It was registered and defined by NSF 49, called the Type C1. And that cabinet actually allows you to do exactly what they had done in their design, and that is have multiple cabinets hooked up to the same mechanical system. It also gave DNA Genotech the ability to run those cabinets with hazardous chemistry just like their bees did. So here's kind of a diagram of what their room looked like, what their lab looked like. They had 4 A2s in there with a lab bench in the middle, and they wanted to add 2 more. What they were able to do was change their specifications from those immobile and inflexible B2 biosafety cabinets and replace them with C1s. And in doing so, they didn't have to require a change order in their engineering and design. This is really important because when they went back and told their architect that to keep the B2s they would need independent exhaust systems, their architect came back with a number that was around like 300,000 Canadian dollars just to change the design. That does not include brick and mortar. That does not include ductwork, installation, or any materials. That was just a change in the drawings that you saw in those first couple slides. So by providing them with something that met their needs but was much more flexible and allowed them to keep their own design, they were able to save a pretty big ticket when it came to the cost of just opening and moving into their laboratory space. And I believe here I have a picture of what that lab looks like now. So you see the 2 cabinets that are closest to the camera here are those C1s, and you see their ductwork up above. The next case we're going to look at is Creighton University. So this is what's going on for today's needs. Creighton was in a tough spot back in 2015. They were they were challenged by the community of Omaha, Nebraska, but also by their Board of Regents to look at reducing energy costs specifically. So they started this energy savings committee. It was an 8-person team, and they were tasked with finding projects on campus that would have a ROI of 5 years or less or better. And they'd already gone through and found, going to T5 lighting and more energy efficient lighting, day lighting in some cases, going to geothermal pumps for heating. They'd found a lot of those low-hanging fruit. And what was important was also that when it came to their science buildings, they wanted to improve or boost this environmental consciousness, but the big deal was they couldn't sacrifice safety. And they even had a safety person on this committee. So they did some research, they did some looking around, and they came across this Type C1 Biosafety Cabinet. And I guess I should preface this by saying their biosafety person came around and said, well, what if we replaced all of their B2s? And they saw that this was kind of a winner from the start. Each B2 biological safety cabinet, I talked about how strict of an exhaust requirement they had on the previous study. On this one, what they were looking at, again, was that ROI and the safety perspective. Each B2 in 15 years uses about $100,000 in air cost alone. So it's pretty significant, and they had at least 12 that were coming up on 15 years of life. So they knew they were going to need to be replacing these cabinets anyway. And they wanted to know if they could replace these B2s with C1s. And what they were able to find was that they could actually replace them and run those C1s in a recirculating A mode. So they didn't even need the chemical protective nature of the B2s to begin with. That was just wasted air and therefore wasted money. So here is a somewhat fuzzy image of one of the recirculating Type C1 cabinets at Creighton University. And again, what was important about this, they saw that replacing the B2s or disconnecting those cabinets was a winner idea from the beginning. When they actually ran their calculations on their first 12 cabinets, they showed a 2.6-year ROI and that they were going to realize an annual savings of over $50,000. What they were really captivated with, though, was the fact that this new type of cabinet is flexible, it saved money, but it actually maintained and increased safety within their laboratory space. So for them, it was a win-win-win that really propelled the university from being a safety-oriented to a environmental conscientious university.
The Purifier Axiom Class II Biosafety Cabinet's 3-piece work surface looks different than any other Class II BSC. The Chem Zone, aptly named for its ability to handle microbiological applications involving chemistry, is a direct exhaust work center. Personnel protective air flowing into the cabinet and downflow air flowing over the side surfaces of the interior, colored blue, are recirculated through the cabinet's supply air system. Chemical vapors should not be introduced in these airflow areas. Air in the column above the Chem Zone, colored red, is exhausted from the cabinet in a single pass. When the Axiom is in its recirculating A mode, this exhaust air is simply returned to the lab through the exhaust interface. When in ducted B mode, chemically contaminated exhaust air is safely removed from the laboratory. A Type A BSC is not designed to handle hazardous chemistry. Type B2 BSCs can, but exhaust massive volumes of expensive room air in the process. The Axiom most closely resembles the Type B1 internal airflow. However, to work safely in a B1, the operator must be trained and work behind an invisible, moving line known as the smoke split. The Axiom Type C1 is the only cabinet that reduces energy consumption while containing chemicals and is safer and easier to use because it does not use a smoke split.
So as the video illustrated, what the cabinet's design was for, obviously, as a biological safety cabinet, is safety. This cabinet was specifically designed and was accepted for applications that were using both hazardous biology and hazardous chemistry, but to serve the needs of scientists in the future and with their flexible lab design and safe lab design, we wanted to make sure that the cabinet was capable of being flexible with that building installation. So speaking of the flexibility and having an eye to the future, let's look at our last case study here, which is looking at flexibility from the ground up. And I'm actually going to use, to illustrate the purpose of this equipment and this thought process, is actually a building that Matt has jurisdiction over, and that's the University of Nebraska-Lincoln's Veterinary Diagnostic Center. So this newly constructed building houses several laboratories, and I believe they just moved in the middle of last month. But it's also, so under the jurisdiction of the University of Nebraska-Lincoln, it's also the state of Nebraska's reference laboratory for veterinary diagnostic medicine. So, you know, a bunch of cows go down ill, or, you know, maybe there's an outbreak of avian virus or whatever. All of those specimens would be sent to this laboratory for diagnosis, and then go to the state of Nebraska, or if it got elevated at that point, CDC, USDA for treatment purposes. When they were designing and looking at this building, and this is where Matt's experience and expertise comes into play, they wanted to look at having a building that would meet the needs that they have right now, but also would be energy efficient, would be safety, which is obviously a big thing, but also the building would last for them into 20, 30, 40 years. So I'll show you some screenshots of some documents that I received. Here you can see a bit of the equipment list that was sent out for bid, and you'll see that from the very beginning that they had already designed or started specifying and designing the building around a flexible biosafety cabinet fume hood configuration. So they had cabinets that were the A2 type, the type C type. They have fume hoods and laminar flow cabinets. So they had already started looking at what would their engineering controls need to be now, but the inclusion of that type C shows that they were thinking that this may need to change in the future. We need to be ready to go if the mission of this facility changes down the line. So here's some symbols, and the reason these are important is I'm going to show you a couple of floor plans of several of their laboratories and how they used and thought about this from a process standpoint. So here's the Histology Lab, and this is going to be pretty much a straightforward processing tissue culture lab, or like I said, Histology Lab, and they built it knowing that they're going to need an area for preparation of work. You have a single fume hood off in the corner. And then here you also have the highest density of these flexible cabinets, but you see 3 ducted biosafety cabinets here in labs that are right next to each other. So from here on the start, they knew that they were going to begin with processes that could be using benzene, formaldehyde, xylene, higher levels of chemistry than you would normally find in a biological or microbiological laboratory. So they knew they were going to start with those cabinets ducted, and that's where these type Cs went. And this is an image of one of their cabinets installed next to some specimen storage spacing. And then you have the virology, serology, and bacteriology laboratories. So these are pretty much cookie-cutter labs. You can see that you got quite a bit of floor space here. The blue boxes, again, these are the type A biosafety cabinets. So this is typically the workhorse of your microbiological laboratory. It's no surprise that there's going to be a high concentration of those wherever you're going to have pathogens being worked on. And typically those are not going to be ducted areas or ducted biosafety cabinets, but you have to have a lot of them to process, or especially in a processing laboratory. But also on this floor or on this lab, you have a number of fume hoods. These would be ducted. And then you also have a C1 in the corner on one of the other laboratories. So here's where that ability to modulate or design flexibility comes into play. Because if now you can imagine that red cabinet were a B2 or some other inflexible design, this laboratory with those hoods so far apart would need several different duct runs. That means several different blowers. And when you try and run that, it increases the price tag of the laboratory quite substantially. Furthermore, with those Bs, they have to run in a ducted mode. So if this cabinet or this lab's need ever changes, they can disconnect any of those C1 cabinets, and they basically become blue cabinets. And when you do that, you end up saving $50,000 over the life of the cabinet, and that's per unit. And this is just an image of that laboratory, and you can see down the row on the right-hand side, multiple A2s that are stacked back on each other. Just showing that these are, I believe, 6-foot units, so the biggest and most workspace you're going to get. This is completely protected for any hazardous biology work. So we wanted to talk about adoption of flexibility, adoption of good lab practices when you're going into design, specifically from the biological safety cabinet standpoint. How can that adoption for flexibility help the lab? With the case of a C1, it can lower upfront costs, and it does that by reducing costly over-designing or purchasing of new equipment due to operational changes. If you buy a B2 and then all of a sudden you no longer need chemical protection, that cabinet's always going to run that level, so you're wasting tons of money on the back end. But then also, if you want to save money, you're going to have to buy all new types of cabinets. Flexibility in that design point really reduces your total costs from an upfront standpoint as well, which you can also look at, again, going back to the example I used at the beginning, looking at vacuum networks. Your safety officer, say Matt, walks into your laboratory and he sees that a guy using E. coli and salmonella in one lab is hooked up to a vacuum network that is doing sterile tissue culture in the other, and they're hooked up to another lab that also is working with regenerative medicine lines. And then all of a sudden, the guy using regenerative medicine lines gets cross-contamination, and all of his costly cell cultures are dying. He's going to tell them, we'll rip out this network or stop using that network, and now we're going to have to install separate aspiration systems all the way across. You've now paid for a very expensive vacuum network that's now completely useless. So same kind of a thought process going there. You want to avoid costly changes, especially during construction or innovation due to poor communication and flexible designs. One of the things Matt talked about were people. Making sure that the design phase has the right people on board and that everyone is consulted can do a lot to mitigate engineering change orders, which, as I expressed, like with DNA Genotech, was going to cost them $300,000. Canadian, there was another customer that we have worked with in New York. Similar thing, they were looking at either redesigning for 6 B2s or incorporating the C1. When they went to their engineer, it was $1.5 million that they were going to have to do. Again, just for drawings. This is just for those architects' expertise in changing ductwork on paper, not even getting into the actual implementation phase. So those adopting that flexibility or being able to accept and see change down the road can go a long way in reducing the money that's going to take to get your lab up and running. And then ultimately, I mean, everyone likes to lower lifetime operational costs. It's really hard for a laboratory or a lab manager or laboratory people in some cases to see 15 years down the road. But when you look at or you go to the finance people and you can tell them that we can save, if we do this, we can save $500,000 over 15 years or $1.5 million over 15 years by adapting and adopting new technology into the laboratory or into the process, in my experience, ears perk up at that point. And we can do that by going to efficiency design, modular design, but really want to harmonize what's going on. Sometimes it's just a different blend of what's used in the past to make the laboratory not just more efficient, but also safer. And all of that leads to an increase in efficiency. And what's great about efficiency is, in today's world, companies, laboratories are all the same. They're asking the same amount of people to do more work. And the only way that'll happen is by increasing the functionality and output of the laboratory and the people that use that laboratory. So bygone are the days of rigid construction that requires anchorage to hard lines and hard facilities. Laboratories are becoming much more fluid in their design as a result of the fluidity of what they're tasked with doing. So we ask, what does the lab of tomorrow look like for you? The last couple of slides, which I believe you'll have access to, are going to have several different resources that will help guide you or your design team through the process of getting your lab up and running. So I welcome you to take a look at those, and I believe that is the end of this presentation.
Thank you, Matt and Brian, for your informative presentations. It is time for Q&A. If you have a question you'd like to ask Matt Anderson and or Brian Garrett, please do so now. Just click on the green Q&A button at the lower left of the presentation window, type your question into the box that appears on your screen, and click on the send button. We'll answer as many of your questions as we have time for. So let's get started. Our first question is, Matt, how did your design team, or how did your team find the architect and lab planning firms with lab design experience?
I think predominantly we've looked at other institutions and when they have built new facilities and found out what teams they have used. I know there's specifically with the Vet Diagnostics Center that Brian talked about. We did find the diagnostic center staff went and visited a few other diagnostic centers and to get some ideas, and then researched architects and firms, design firms that had experience with those buildings.
You both spoke a lot about engineering controls, hoods, and biosafety cabinets. Have you come across, or are there other examples of places where flexibility should be considered? And Matt, would you want to address it first?
There can be. I think one of the examples would be, as Brian did point out, with the aspiration systems, and vacuum systems. Those are some of the things that can be thought about when you're designing things, whether you want to have that centralized or if it's going to be specific to each lab and isolated. That can provide some flexibility. Another way to provide some flexibility that we actually did implement in the Vet Diagnostics Center was to put a lot of the utilities and things up above so they were drop down, so the room could be rearranged and some of the furniture was more mobile, and so the room could be reconfigured in the future if the needs change for the space.
And Brian, would you want to discuss that too, or?
Yeah, absolutely. So something else we'll look at, we talked about predominantly about biological safety cabinets, but also look at water systems, water purity. Oftentimes for a small-scale lab can be point of use and can actually be costly from a cost perspective, but also from a quality perspective, or negative from a quality perspective if you have a large single source point of water that's central to a large facility. By the time that water gets to the end of the line, it may not be the type 1 water you need for your high-grade chemistry or HPLC and that kind of work. So in some cases, the building's going to have water purification systems, but for certain instances, certain uses, point of use laboratory water can be required or necessary. Along with that, glassware washers. Some places, like I know vivariums, they get along just fine with having one large, giant rack washing system. That works great. If you have one chemist, though, that's, again, doing high-grade chemistry and needs a high degree of control over the purity of the water and the glassware that comes out of that, he may need a separate system So to force them into a central or large grade washer for an entire floor would not be feasible. Those are just two more examples. Fume hoods, mixing ducted fume hoods with ductless fume hoods can also limit energy consumption, limit the amount of money spent per year on that valuable air that we talked about kind of with biosafety cabinets. So again, all of those designs, any part of the process that can differ from laboratory space to laboratory space or researcher to researcher should be looked at very specifically to determine what's best for that laboratory going forward.
Matt discussed a collaborative design approach. How soon in a project should various disciplines be approached about their needs? Brian, would you want to talk about that one first, or should we give it to Matt?
Matt, you want to take a whack?
Sure. I would say as soon as possible. I mean, you can start talking about some of these things in the early stages where you're just, doing some brainstorming on planning. There may be a chance for that may be the earliest chance for the lab workers to be involved in a discussion to talk about the procedures they're doing and things, new technology they may see that they want to incorporate. But yeah, I would say as soon as possible, get people involved.
And Matt, this next one's for you. How do you raise funds to start off a small-scale laboratory? Is that something that we could, do you think, talk about in this frame here, or should we save that?
Well, I guess I'm not sure what small scale means.
We could
if you're
maybe, and the person could be more specific. Would you like that?
Yeah.
So this next one's for you too. Hi, Matt. I've been looking for some references for PPE requirements recommended for different categories and types of labs. Can you recommend any resources?
There's lots of resources out there. If you're looking at biological labs, I would recommend the Biosafety in Biomedical, Microbiological and Biomedical Laboratories manual. That's a book that's put out by CDC and NIH, and it's you can access it on CDC's website. There's also Prudent Practices in the Laboratory is a book that's put out as well, and reference document. There are a lot of academic institutions that provide their guidance free on their websites, so that's another resource that I would suggest taking advantage of.
Okay, great. And while we're waiting for additional questions to come in, I would like to once again thank Matt Anderson and Brian Garrett for their presentations. Do you have any final comments? Maybe Brian first? Sure.
In all the projects, new laboratory whether it's a redesign, a reformat, or new construction, what I've often found is that the more questions that can be answered in specifics about the research being done, the number of researchers you want to house, how big do you want to get in a sustainable for your institution, the more of those questions that can be flushed out before you even get to talking to architects, engineers, lab planners, the more streamlined the whole process is going to be. So Matt discussed, making sure you build the right team and you look at things from a systemic and a process point of view. All of those questions are going to make, or those answers, having that data is going to make the job for your architect and your design team a lot easier. And also, from a practical standpoint, the less they have to change down the road, the more likely you are to stay on budget and for your building to be completed on time. So I think those are all great things, and I know with Matt's experience, he's looking for those real-world tips. Having that stuff up front makes everything a lot easier.
And Matt, do you have some thoughts to share?
Yeah, I think one thing I wanted to share is just to make sure that once you are involved in the project, to try to stay involved, because sometimes once you're beyond the design phase and the design has been settled and construction starts, you tend to back off a little bit sometimes, but sometimes there's things that come up through construction, through meetings that need to be decided.
more or less on the spot, and it's important to make sure that you're still involved in that process and can provide that input when it's requested from the design firm or from the construction personnel. So that's all.
Well, great. Thank you both once again. I would also like to thank our sponsor, Labconco, for making today's educational webcast possible. This webinar has been approved for continuing educational credits. Please click on the CE button at the bottom left corner and follow the process to receive your credits. Before we go, I want to let everyone know that today's webcast will be available for on-demand viewing through March 26, 2018. You'll receive an email from LabRoots letting you know when this webcast will be available for replay. Please share that announcement with your colleagues who may have missed today's live event. That is all for now. Thank you for joining us. We hope to see you again soon. Goodbye.